In a photoelectric effect experiment, a metallic surface of work function 2.2 electron volt is illuminated with light of wavelength 400 nanometer. Assume that an electron makes two collisions before being emitted, and each collision 10% of additional energy is lost. In first part of the question, we need to find the kinetic energy of this electron as it comes out of the metal. In the second part of the question, we need to investigate after how many collisions the electron will be unable to come out of the metal, right? So let us first analyze the question. In question, we are given work function of the metal, right? We are also given the wavelength 400 nanometer or 4000 angstrom. And here we are given the electrons make two collisions before being emitted. In each collision 10% of the additional energy is lost. In previous questions, we have never considered collision of electron. We use simply Einstein photoelectric equation without considering the energy lost during collision. But in this case, we need to take care of this energy lost, right? So first of all, what we need to do, we need to find the initial energy, right? Initial energy means we need to calculate the energy of photon. We can calculate the energy of the photon by using the formula Sc divided by lambda, right? So this formula we need to use. We know while using this formula, we need not to multiply h and c, because h is Planck constant, c is velocity of the light, and these quantities are constant always. So we need to only apply the multiplication value of this Sc, right? And we know this value is 12400, right, divided by lambda in angstrom. But we are given in wavelength in the nanometer, so we can modify this formula. We can write 1240 divided by 400, right? In place of angstrom, we have written nanometer, and that's why we have written the multiplication of these two quantities as 1240, right? We can calculate this value, and this is the initial energy that is incidenting on the metal surface, that is 3.1 electron volt. Now we need to consider the collision of the electron, right? Let us calculate the energy lost in first collision. It is given 10% energy is being lost. So we need to calculate 10% of this value. So this is 3.1 multiplied by 10 by 100. This is equal to 0.31 electron volt, right? Now we need to find the remaining energy of electron. Remaining energy of the electron should be equal to 3.1 electron volt minus 0.31 electron volt. So this value comes to be 2.79 electron volt. This is the energy left with the electron after one collision, first collision, right? Now let us consider the second collision. Again, we need to consider the 10% loss of energy. So we need to find the 10% of this value. So we can now write 10% of this value as 2.79 multiplied by 10 by 100, and this is 0.279 electron volt. Now the energy left with the electron, that means the energy, total energy lost in the process of the collision, you can say. So let us calculate the total energy lost in two collisions. Okay, this energy lost in the first collision, this energy lost in the second collision. So let us calculate. This value is 0.589 electron volt, right? Now let us apply conservation of energy. We know energy incident on the metal surface through the radiation is Sc divided by lambda. This energy is utilized in the work function, right? Work function, you know, that is the energy required for electron for coming out of the metal surface. So part of the energy will be utilized work function. Second part of the energy is utilized as a kinetic energy, and third part of the energy is energy lost in collision. This is this one, right? So we can write like this. And we know this value. We have calculated this is 3.1 electron volt, right? So this is 3.1. Work function 2.2. Kinetic energy we need to calculate. Energy lost during collision, this one. So let us substitute this value, right? And here kinetic energy of the electron after two collision should be equal to 0.31 electron volt. So this is the first part of the question. Now let us move to the second part of the question. Second part of the question, we need to calculate how many collision the electron will be unable to come out of the metal. When energy of the electron is less than the work function of the metal, electron will be not able to come out of the metal. So let us calculate the energy left with the electron after many collisions. Here the previous part of the question we have taken care of the two collisions. We have calculated the energy left with the electron after two collision is this one, right? 2.79, and energy lost was this one. So let us calculate the energy remaining with the electron after two collisions. So let us calculate total energy remaining after second collision. This is 2.79, this value 2.79 minus 0.279. This is the scenario after second collision, and this value is 2.511 electron volt, right? Now again 10% energy will be lost. So let us calculate the energy lost in third collision. That means we need to again calculate the 10% of this value. Energy loss in the third collision should be equal to 2.511 multiplied by 10 by 100, right? And this value is 0.2511 electron volt, right? So this is the energy lost in third collision. Now let us calculate the energy of the electron after third collision, that is the remaining energy after third collision. So we need to subtract this value with this value, right? So this is the subtraction. This value comes to be 2.2599 electron volt. So here we can observe the energy of the electron after third collision is slightly greater than the work function, right? So let us move to fourth collision. In fourth collision, energy lost in fourth collision, again 10% of this value. This is a 10% of this value. This comes to be 0.2259 electron volt. So let us calculate the energy of the electron after fourth collision. We need to subtract this value with this value. So remaining energy should be equal to this one, 2.034 electron volt. We can observe here this value is less than work function of the metal. That means after fourth collision, electron does not have enough energy to overcome the work function. That means it will not come out. Now let us move to next illustration. A light source emitting three wavelengths 5000 angstrom, 6000 angstrom and 7000 angstrom has a total power 10 to the power minus 3 watt and a beam diameter 2 into 10 to the power minus 3 meter, right? The power density is distributed equally amongst the three wavelengths. The beam shines normally on a metal surface of area 10 to the power minus 4 meter square and having the work function 1.9 electron volt. Assuming that each photon liberates an electron, calculate the charge emitted per unit area per second. Okay, let us analyze the situation. In this case, we can observe light source emitting three wavelengths 5000, 6000 and 7000. But in the previous problems which we analyzed, we have monochromatic radiation incidenting on the metal surface. So we need to consider what is the effect of the three wavelength incidenting on the metal surface. Also, we are given here the power, total power and beam diameter, and it is also given the power density is distributed equally amongst the three wavelength. We are also given the work function and also given the area of the metal surface. Okay, so first of all, we need to find the threshold wavelength. Why we require threshold wavelength? Because we know the threshold wavelength is the wavelength of the incident radiation above which the photoelectric effect is not possible, right? That means if incident radiation wavelength is less than the threshold wavelength, then only we can have the photoelectric effect. So first of all, let us check the wavelength that will cause the photoelectric effect. We have the three wavelengths given. Okay, for this we need to find the lambda max. Lambda max is the threshold wavelength, for which we know the formula of the energy of the photon, that we have E equal to Sc divided by lambda. If we take this as a threshold wavelength, or we can write lambda max, and here we need to substitute this value as a work function. That means if we take wavelength as a threshold wavelength, the energy should be just enough to overcome the work function. So here we can write lambda max equal to Sc divided by W. Right? W is a work function. So let us write the expression like this. Okay, we can rearrange. Lambda max will be equal to Sc divided by W. And we know the multiplication of these two terms, because wavelengths are given in the angstrom. Here we can take this multiplication equal to 12400, and work function in electron volt is 1.9. So this is the value of the lambda max, and lambda max is the threshold wavelength. This is equal to 6543 angstrom. Now we can observe the wavelength 7000 angstrom is greater than this value. That means this radiation or this wavelength is not having enough energy to emit the electron from the metal surface. So we can say the wavelength 5000 and 6000 wavelength will cause the photoelectric effect. Now we completed first part, first task of the question. Now we are given the beam diameter. Beam diameter is 2 into 10 to the power minus 3 meter. Beam radius will be equal to 1 into 10 to the power minus 3 meter. If we calculate the area of the beam diameter or area of the beam, and we are given the power of the radiation, we can find the energy flux or energy density. So let us calculate the area of the cross section area of the incident beam. This is equal to pi r square. R is 1 into 10 to the power minus 3 meter, right? So this is the beam cross sectional area. Now let us find the energy flux. Energy flux is nothing but intensity of the radiation. This is power divided by area of the cross section. Power is energy per unit time, that is joule per second, and this is meter square. We can simply write in term of the watt per meter square. It is simply intensity. So we can write I equal to 10 to the power minus 3 power divided by this area. Okay, so we got the intensity, that is equal to 10 to the power 3 positive divided by pi watt per meter square. Now let us move to the next part of the question. It is given the power density is distributed equally amongst the three wavelengths. That means I1 equal to I2 equal to I3, that is equal to I by 3. So we got the intensity of the radiation associated with the each wavelength. Okay, and this I is equal to 10 to the power 3 divided by pi. So this is I1 equal to I2 equal to I3 equal to 10 to the power 3 divided by 3 pi watt per meter square. Okay, now move to the next task. We need to find the energy of the radiation or photon associated with this wavelength and this wavelength. We need not to consider this wavelength, because this wavelength is greater than the threshold wavelength. So let us calculate the energy of the photon of the wavelength 5000 angstrom. Okay, and we know the formula of energy of the photon as Sc divided by lambda, and we know Sc multiplication when wavelength is given in angstrom, that is 12400 divided by lambda in angstrom. So we can write 12400 divided by 5000 in electron volt, and we can calculate this value. This value will be equal to 2.48 electron volt. Okay, we can change this energy value into joule by multiplying this value by 1.6 into 10 to the power minus 19. This value will be in joule, right? If we multiply again, this is approximately equal to 4 into 10 to the power 19 minus 19 joule. So we got the energy associated with the wavelength 5000 angstrom, right? Now we can calculate the photon flux. Photon flux is nothing but number of the photons per unit area per second, right? We know the energy of a photon, and also we have the intensity of the beam associated with each wavelength, this one. So here, if we divide I with this energy of photon value, we will get the number of the photons per unit area per second. That is again called the photon flux. Okay, so N1, let us write this value as N1. N1 is equal to I1 intensity divided by energy of the photon associated with this wavelength, this one. Okay, so this value after calculation will get 2.65 into 10 to the power 20 photon per meter square second. Okay, now we know energy of the photon is written by Sc divided by lambda. Sc is a constant term, we know. That means energy is inversely proportional to lambda. We can write E1 by E2 equal to lambda 2 divided by lambda 1. Okay, now we can write photon flux for lambda 2 because we have calculated photon flux for lambda 1. Now we can indirectly calculate the photon flux value for lambda 2. We can write this lambda 2 is equal to, that is a photon flux for lambda 2 equal to N2. Let us write N2 equal to I2 divided by E2. We know I1 equal to I2. So let us write this value, right? And we know we can write now E2 equal to E1 multiplied by lambda 1 by lambda 2. We can rearrange this relation, right? Because we know I1 equal to I2 equal to I3, and in place of I2 we can write I1. So here we can observe I1 divided by E1 here is nothing but N1, this value. So we can now write N1 multiplication lambda 2 divided by lambda 1, and this is a N1 and this is lambda 2 divided by lambda 1, and this is finally after calculation we get 3.2 into 10 to the power 20 photons per meter square second. Okay, so we got the value of N1, also N2, and it is also given each photon is responsible for emitting 1 electron. So here we can calculate the value of the number of the electron emitted through 5000 and 6000 wavelength radiation. So let us find the number of the electron or electron flux. Electron flux is the number of the electrons emitting per unit area per unit time. So this is the summation of these two values, N1 and N2. So let us sum these two values, and this after summation we will get the value 5.88 into 10 to the power 20 electron per meter square per second, right? Now we can calculate the charge emitted per unit area per second. These are the electrons per unit area per second. That means if we multiply this quantity by 1.6 into 10 to the power minus 19, we can find the charge emitted per unit area per second. So let us multiply this quantity by 1.6 into 10 to the power minus 19, like this. Okay, this value After calculation, we will get 94 coulomb per meter square second. This is the required value. Now let us move to next illustration. The question is, in a photoelectric setup, a point source of light of power 3.2 into 10 to the power minus 3 watt emits mono-energetic photon of energy 5.0 electron volt. The source is located at a distance of 0.8 meter from center of a stationary metallic sphere of work function 3.0 electron volt and radius 8.0 into 10 to the power minus 3 meter. The efficiency of the photoelectron emission is 1 for every 10 to the power 6 incident photon. Assume that the sphere is isolated and initially neutral and that photoelectrons are instantaneously swept away after emission. We need to find number A, calculate the number of the photoelectron emitted per second. Number B, it is observed that the photoelectron emission stops at a certain time t after light source is switched on. Why? We need to investigate, and in the C part we need to calculate this time when photoelectric emission stops. Okay, so let us analyze the situation. What is happening? We are given the power of the point source, that is 3.2 into 10 to the power minus 3 watt, right? And we are also given the energy of the photon 5.0 electron volt. We are not given the wavelength, directly given the energy of the photon. The source is located at a distance 0.8 meter from center of a stationary metal sphere. That means we need to find the intensity of the radiation at a distance 0.8 meter. And we know intensity equal to power divided by area. And this is a point source, and we know for point source the energy density has the spherical symmetry. So first of all, we need to find the intensity at a distance small r. This is a point source and this is a metal sphere which is placed at a fixed position at a distance small r, right? So let us consider power is P, and we can calculate the intensity I equal to power divided by area of the sphere of radius small r, that is P divided by 4 pi r square. This is the intensity at a distance small r. Now let us calculate the energy received by the metallic sphere, and we know the energy received should be the intensity multiplied by area of the projection of this sphere, right? Area of the projection of this sphere should be circle of radius capital R. So energy intercepted by a metal sphere per second equal to intensity multiplied by area of projection of the sphere, this one, that is radius of circle of capital R. So here we can write I, this value, multiplied by pi capital R square. Pi and pi will get cancelled. So we get the energy intercepted by metallic sphere per second equal to P R square divided by 4 small r square, right? Now if E is the small e is the energy of a single photon, if we divide energy of a photon with capital E, that is capital E divided by small e, will give the number of the photon incident on the metal surface per second, because small e here we taken the energy of a single photon. But in question we are given the efficiency of the photoelectron emission is 1 for every 10 to the power 6 incident photon. Here it is not given one photon is releasing 1 electron. So we need to consider the photon efficiency. So here we can calculate the number of the electrons incident on the metal surface, number of the electron liberated from the metal surface per second. That should be equal to small n, let us call this a small n, that is equal to photon efficiency, say eta, and this is capital E divided by small e. So let us write this term. We have calculated this value, that is the energy incident per unit time, right? And this is the energy of a photon. So this value comes to be like this, and this is eta p r square divided by 4 small r square e, right? This is the number of the electrons ejected from the metal surface, number of the photoelectron ejected from the metal surface. Now we know this value. This is 10 to the power minus 6, because we are given 1 for every 10 to the power 6 incident photon. That means here 1 photon is given 10 to the power minus 6 electron, or we can say 1 photon is responsible for 10 to the power minus 6 electron. So we have the efficiency value eta equal to 10 to the power minus 6. So we can substitute the value. After calculation, we will get the value 10 to the power 5 electrons per second. We got the answer for the first part. Now let us move the second part. In second part, it is given, it is observed that the photoelectron emission stopped at a certain time, capital T, after light source is switched on. Okay. After some time, photoelectron emission stops. What happens when electron emit from the metal surface? If electron emit from the metal surface, that means the metal surface or metal sphere in this case will be positive. That means the emission of the electron from metal surface or metallic surface leaves a positively charged, right? As the potential of the sphere begin to rise, that means the sphere was initially neutral. When electron start releasing, the sphere getting positively charged. That means the positive potential of the sphere start increasing. That means it start attracting the emitted electron. The emission of the electron will stop when the kinetic energy of the electron is neutralized by the retarding potential of the sphere, right? So here we can write EV equal to K max. V is the potential of the sphere and K max is the maximum kinetic energy of the electron. That means potential of the sphere should be equal to K max divided by E. Okay, and we have the Einstein photoelectric equation, that is K max equal to HF minus W. That is the incident energy minus work function. And here we are given the energy incident and work function. So let us substitute these values, that is equal to 2 electron volt. That means this value should be equal to 2 volt. And we know the potential of the charge sphere is given by 1 upon 4 pi epsilon naught charge divided by radius, right? And charge should be equal to N multiplied by E. N is the number of the electron emitted and E is the charge of the electron. So we can write V equal to 1 upon 4 pi epsilon naught Ne divided by capital R. Okay. And this value we know this should be equal to 2 volt. So let us substitute this value, and from this expression we can find the value of the capital N, and capital N here is the total number of the electron emitted from the sphere, right? Now we can substitute the value. We know this value 4 pi epsilon naught is equal to 1 divided by 9 into 10 to the power 9, and E is 1.6 into 10 to the power minus 19, and this value is given, radius is 8.0 into 10 to the power minus 3 meter. So let us substitute this value. After calculation, we will get this value as 1.11 into 10 to the power 7. Okay. That means the photoelectric effect will stop when 1.11 into 10 to the power 7 electron have been emitted, right? But we know electron emitted per second, which we have calculated in the previous section, was 10 to the power 5 electron per second. So from this value we can find the time. If we divide this quantity by 10 to the power 5, we will get the time when photoelectric emission will stop. So T should be equal to 1.11 into 10 to the power 7 divided by 10 to the power 5, and this is equal to 111 second approximately, and this is equal to 1.85 minutes.